Let's try again. All right, how we doing? Here we go. Oh man, that was rough. Hello, hello, hello. That was rough. Hello, hello, hello. Okay, so we're back. That was brutal. So yeah, I didn't realize, but my stream had basically died for the past 15 minutes, and I had no idea. I was so engrossed in this question, this problem, trying to explain how it works. Sorry about that. Yeah, so here's what I was doing. Um, let's see, can you see my thing here? So let me try explaining again what it was. The idea was that I would have bits that I would shift. I would take this bit and this bit, and I would recursively eliminate these bits, which would take logarithmic time. Then this bit I would shift down to the left using these operations. So it would be, first I could flip this bit once, then I can delete this one, then I could flip this bit and delete this one, then I could flip this bit and delete this one, and then finally I can flip this bit, and then I can delete it at the end. And all of those computations that are required to do that can be done separately and saved, how much time it takes to do all those, how many operations it costs. And so it would be a logarithmic number of operations to perform this whole routine and a logarithmic amount of operations to perform the subroutines. The subroutines are going to be flipping a bit to one and moving it to the left a certain amount, which is required for, which is required. And then also, which actually is this one. So it's required for calculating this part. And then this part is going to be, you flip the bit to one, move it to the left, and then you use that to delete that bit and basically shift it to the right. So shifting all the way down to the left allows you to figure out how to shift to the right one, and then shifting to the right one several times allows you to figure out how much it takes to just delete a bit altogether. So these three different routines are all related to each other, and they can all be computed together kind of inductively. And that's the idea. And unfortunately, my stream died before when I was trying to explain all this. And that's a bummer. That's a bummer. Let me get the chat here and just say that I didn't mean to not be able to explain all that. So that's the idea. Let me see if I can implement it. So that's what I was working on, and it's really a bummer that I spent like 15 minutes explaining this, and the stream was dead the whole time, and I had no idea. So let me first try to compute each of these. It's going to be. I could do the top down recursion first. So we'll do recurse. Do the top down recursion first. Actually, it's fine. We could do either way. We're gonna recurse on n, I think. Yeah. Excuse me. Recurse on n. And the way this is going to work is constant, or actually, we're not going to, it's going to be a copy int num or val, int val. So return, so that's going to be int total is 0. Total plus, we're going to have also this auto double reference self. Excuse me, self. No. Yeah, I think it's self. And this auto double reference self is what it is. Self of smaller value. It's going to get modified. So first bit, so const int sig bit is going to be stood. I think it's just built-in CLZ. 32 minus built-in CLZ of val. And then bit shift that by 1. And if there's 3 leading zeros, that's the 31st position, 30th position, 29th position, 28th position. The number I would get would be 3 leading zeros minus 3 is 29. And I'd bit shift 1 over by 29. I think it's 31 minus CLZ. Yeah, because 1 already starts out at the 0 index. So if you had 31st position minus 1 would give me 30th position. And if I shift over 30 times, if I shift over 0 times with the 0th position, 30 times will put me in the 30th position. Yeah, that's correct. Yeah, that's the most significant bit. Then you can do const int sort of removed or flipped or sig removed is going to be val XOR with the sig bit. Then we say const int pen ultimate sig bit is then 1 bit shift 31 minus built-in CLC sig removed. We'll say pen sig bit. Or just next sig bit. So that's the next significant bit, most significant bit. And then we can say val equals val or sig removed. You can actually even do, you don't even need that. This could be constant. This could be sig removed with the next sig bit also removed. So it's the cost to remove, once those 2 significant bits are removed, zeroing out the rest of the values. That's what's going to be added to the total. And the way this is going to work now, we're going to say we want to bit shift to the left this next sig bit. Constant sig bit index. This could be a char, by the way. Doesn't have to be an int, but that's fine. And then this is going to be next sig bit index. Oops. Okay. Next sig bit index. All right. So got sig bit index, and then we got next sig bit index. All right. Now, what I was suggesting was shift next sig bit to the left after clearing the right bits. Also, are we okay here? We are. Hello, bro. Can we connect? Please also explain the logic of line by line explanation. What's up, Adil and Nadim? How's it going? Welcome, howdy. Yeah, we can, for sure. I'll explain the logic shortly. Although, yeah, I could do that. Let me keep going here, though. Let me try to code it first. Okay. Yeah, I'll come back and explain it. So we're going to shift the next sig bit to the left after clearing the right bits, which is going to take the shift bit right amounts. So we're going to do shift bit right repeatedly on the next sig bit index. And we're going to do for int I equals next sig bit index. Starts off at that point. And we're going to say I is less than a certain amount, increment I, take the total, plus equals this value for I. And yeah, if you want to add me on anything, you can. Here's my profile, and you can follow me there if you want. You can add me on LinkedIn if you want. Whatever you want to do is fine. So okay, we're gonna go shift bit right. It's not gonna shift bit right. We're gonna shift bit left rather. Oh yeah, I made a mistake. I need to have the shift bit left, not shift bit right. We'll move bit to index. To shift the bit to the left. Actually, that's a good question. I forgot what I need to do that. Oh no, I know what to do. Yeah. I can immediately take the bit to the left, flip it to a 1, and then I need to erase. Okay. Shift bit to the left after clearing the right bits. So repeatedly after clearing the right bits. So the way this is going to work is we're going to have +1 to flip the bit to the left, and then we're going to clear single bit on I. So +1 is going to flip the bit to the left, and then we're going to clear this single bit, and then we're going to flip the bit to the left and clear the single bit, and do that repeatedly. So I'm not going to shift by right. Clear single bit is going to be flip single bit. That's what it is. And we're going to do that until we get to, there's the significant bit index. we're not going to do that index. We're going to do the index right before it. So it's going to be sig_bit index. Yeah, flip the bit to the left and delete this one. Flip the bit to the left and delete this one. And we keep doing that really just before the sig_bit index. At the sig_bit index, so at the sig_bit index, we're going to flip that one later, but there's going to be another bit before it. We're not going to add one and then delete. Well, actually, you can. Actually, you can go all the way up to the sig_bit this way. That's actually correct. The sig_bit index is actually going to, once you get to the one right before it, it's actually going to flip the sig_bit off, and then we're going to delete the bit there. So this is actually exactly what we need to add. And that's it. That's the recursion. Very simple, actually. And this, by the way, this could be optimized too to be a single operation instead of like a whole bunch of operations. This could be a prefix sum, and this could be made basically constant time. I don't think it's necessary to make that so fast, but we can do that. So then, dang, how are we doing on time? It's 17 minutes. Yeah, probably finish this question, I think. So the next thing to do would be calculate the slip single bits and the shift bit to the right. These can be done in a once in a immediately invoked lambda expression. So this will be calc or precompute. And then we're just going to say for int I is 0, I is less than 31, increment I think it's going to be, yeah, int is 0 to less than or equal to 31. We're going to say, so these initially had 0. I think this is going to be I equals 1, by the way. Got these three things we want. Okay, so these are the three different arrays we want to populate. Initially, move bit to index of 0 is going to be one operation. Yeah, in other words, there's the 0 in that spot, we flip to a 1. As an aside, this recursion, the base case is if val is less than or equal to 1, return val. So if val is 0, return 0. If val is 1, return 1. If a val is 2, then you're going to return val is 2. and you're going to return, what do you return a values to? One operation to get 1, 1, 2 operations to get, I think it's 3. 2 operations to get, 1 operation to get 1, 1, 2 operations to get 0, 1, and then 1 operation to get back down to 0. Just to keep it simple. Okay, so assuming we're starting from 0, we move a bit to index 0, we just flip the bit to a 1. Shift bit right of 0. If we're at 1, it's just 1 bit flip. And then flip single bit is going to be also 1. Right, that's what it costs for the first bit. For the next bit, moving the bit to index, well, flipping the single bit of I in relation to move bit to index, and shift bit right, just shift bit right. Okay. So let's start with shift bit right. So shift the bit to the right. You need to, and it's all zeros to the right. You've got to move bit to index I minus 1, and then you've got to add 1. So move bit to index minus 1, and then you flip the bit at index I, which gives you 1 operation. So you do that. So that's shift bit to the right. So move bit to index up to this point is going to be move bit to index of I minus 1 plus 1 plus flip single bit of I minus 1. So in order to move a bit to this particular index, what you're going to do is you're going to move a different bit to the index before it, then you're going to flip this bit on, and then you're going to flip that other bit off, right? So flip single bit I minus 1. Then to flip single bit I minus 1, you're going to shift bit to the right of I, which we just calculated. And then you're going to flip single bit of I minus 1. Okay. Yeah. Well, no. You're gonna move this bit index to the I minus 1 position. You're gonna flip the bit, and then you're gonna flip the single bit. It's the same calculation as this one. Oh, it is, isn't it? Yeah, these are the same. Move bit to index and flip single bit are the same calculations. It's exactly the same. That's interesting. Yeah, what you're going to do is, in order to flip the single bit, you're still going to move the bit to that index I minus 1. Then you're going to flip the bit, and then you're going to flip that bit, flip that single bit, which is just moving to the right several times. Oh, that's interesting. Huh. Wow. All right. Cool. So is that it? Is that all that's required? Immediately invoked Lambda expressions, I think, need to return something. Compiler. Oh, I see. 595. Okay. Runtime error. No. Oh. Well, that's a bummer. Okay. I wasn't expecting that. These need to be larger numbers. That would kind of surprise me. These overflow? I was not expecting that. Okay. Maybe this is the wrong answer. Maybe this reasoning is wrong.